Today I'm talking about generating circuits with generators. I mean digital circuits. First I would like to motivate my choice. Why do I even work with digital circuits? Recently, two Turing Award winners said that the next decade will see a Cambrian explosion of novel computer architectures, meaning exciting times for computer architects in academia and industry. So things will be happening in digital design world. Why is it important for us? We are doing functional programming. So only two people, only one of those is a Turing Award winner, said that the programming language community stands on the critical path on the new golden age of computer architecture. Fortunately, there is an abundance of intellectual challenges that indicate they were on the cusp of a new golden age of hardware description languages. It looks like there are things to be done here. There are some things that are motivating me personally. So one thing is open source, right? For a long time, hardware development tools were completely closed. So recently, there are more and more open tools for hardware synthesis, for synthesis to silicon. So this is great. Another thing that's motivating me is RISC-V. So it's an open CPU architecture developed at Berkeley. So it's very popular both in academia and in industry. Everyone loves it. So I think it's a good motivation thing. Another thing that motivates me is FPGAs, right? So these are those things which are kind of CPUs, but for hardware, right? Like CPUs interpret computer programs, then FPGAs interpret circuits, right? So they allow to treat hardware more like software, where they can be developed in agile way, and they also enable domain-specific acceleration, for example, in the cloud, right? You can just have a FPGA on the cloud to do some stuff for you. What is a digital circuit exactly? So for many of you, probably the first image is some network of gates, but this is a very low-level model, which is not very helpful for many things. So we'll take a little more higher-level approach. So we will think about digital circuits as milli machines, right? So milli machines have some state, which is embodied by this block in the middle there, and this state changes from clock cycle to another, so the time is discrete. And we have two functions. One is the transition function, which says what's the next state after a clock cycle, and another is an output function, which says what is the output of the circuit in the current clock cycle. Okay, so I show you a few examples to show you what I mean. So this is a very simple counter circuit. We have some state which stores the current value of the counter, and then other which can increment the counter. So this is a milli circuit. So the value of the counter changes the same cycle when the input is 1. So if input is 1, the counter increments. If input is 1, it doesn't, which is shown below. On the right, you see typical way it is traditionally described by hardware developers, right, in Verilog hardware description language. And it's you can clearly, I hope, see where the transition function and output function are in this code, right? Here is another variant of the counter, which is a Moore circuit, which means that the output depends only on the state. It doesn't depend on the input. So so it changes its state only in the next clock cycle after the input which is related to it. So if we see that in the first clock cycle the input is 1, so that it's incremented only in the second cycle, right? The last example I want to show you is one with some kind of control flow, right? So you can traditionally express control flow in milli machines as state diagrams, right? And on the edges are the conditions which show you which way in which conditions you change the current state. So this kind of looks like flowcharts, and we programmers don't really use flowcharts anymore. On the right you have how it's implemented, typically using Verilog order hardware description languages. And it kind of looks like a big while loop with a switch inside, right? So no, this is not how we write country programs now, right? So with what we'd really like to do is have some structural way to describe control flow in automata, right? And this is what I decided to do. and I developed a programming language which is called YieldFSM. And what is it's a language for describing media automata, of course. It is embedded in the Clash programming language. Maybe some of you know Clash. It's kind of Haskell for hardware, right? It is essentially Haskell, but it has two different interpretations. It can be interpreted as a normal Haskell program, and it also can be compiled to hardware, to circuits. I use template Haskell for the embedding. So what are the features of YieldFSM? One of those is mutable variables. You can store state in the variables. Another is first order functions, so which can be embedded in any way. And another feature is tail recursion. General recursion is allowed because the stacks is then unbounded potentially, right? We want only bounded stacks because this amount of state in a machine is constant, right? Okay, and the core feature of this language is the yield statement, right? So it's the generator abstraction, right? So the yield statement generates new output of the circuit and then simultaneously advances the clock so that the next statements are using the input values from the next clock cycle. So let's go back to those examples I was showing before, right? So this example for a milli counter circuit. And we see that it's described pretty naturally, right? We have this variable which stores the current value of the counter, a loop which runs forever, and we have two statements inside the loop. The assignment which increments the clock. This extend keyword just means that we extend 1 bit value to a 2 bit value, and then we yield the changed value, right? So we both change the state to +1, for example, if the input is 1, and this changed value is the next output. And in the Moore version, this version which reacts in the next cycle, it's a little more involved, right? So we need to yield the value which was in the state in the current cycle, but then change the state. But after we do the yield, then we are already in the next clock cycle, given the semantics I given before, right? So we need to access the value of the input from before the yield, so it starts using this let statement here. And this pattern, it turns out, is very useful in this language. So I added a syntactic sugar for it. This so-called magic prime. This prime after I means that it's the value of I from before the yield. So in this way, we don't need to use this let anymore. This means the same. Okay, so this is the last example. The next example with control flow. And here we see that we can use normal structural way to describe this control flow. It's no longer a big switch statement, right? So we have a big loop. This first looping is achieved using the continue statement, which works just like in C or other languages like this. Then is another while do until, where of course I use this magic prime to refer to the value of B in the same cycle as was before the yield. And after those two loops, we have a single yield 2, which corresponds to this Q2 state at the bottom, and then we need to go back to the start, so it's just ends the loop. Right, so we see that this control flow and many other useful ways of control flow can be easily described in this language. How this language works, I created a compiler which uses a number of transformations. So which first have a desugaring pass, which for example eliminates loops, replacing them with tail recursive functions. Then we have a lambda lifting, which makes all the functions top level. Then I have a pass called normalization, which is where I transform the code to almost a normal form. And then in the same pass, I remove mutable variables. The next pass eliminates the calls which are not tail calls. Here, the implicit stack is replaced by an explicit one using data types. The next transition makes that each function yields exactly once before making a tail call, so that the functions can correspond one-to-one to states or groups of states in the Mealy machine. Then it's an optimization pass which cleans up the code. And then when we have a group of functions which tail call themselves and each yields exactly once, we can just read the Mealy automaton from that. And this is the last pass. Okay. So it's here an example how that works. I will not show the details of the passes themselves. You can read that in the paper. So here we see how that works for the Mealy counter. We just have one function which tail calls itself, and it increments the value, yields the new value, and uses it as the new state, which is a parameter to this function. The Moore version, as we see, it yields the value which was the parameter, but calls with the incremented value. And the last example with structural control flow compiles as it's easy to see to three mutually recursive functions which use if statements to select which function is then the next state. Okay, so now it's time to see some applications, right? So this whole language I developed. So how does it do in practice, right? So can we do something with it? So first example is pretty simple. Here are this HD 44780 displays. So you probably know those. Even if you never programmed them, you probably encountered them in real life. So those displays have a simple command protocol to work with them. But before you start writing to them, you need to initialize them. There is a sequence of commands which needs to be timed exactly to initialize those displays. Only after this initialization, you can work with them. So normally you work with them using microcontrollers, and then it's easy. But if you try to do this using hardware description languages, traditional HDLs, it is complex. So I found an implementation on OpenCores, and it's quite long. It has 270 lines of code of VHDL. I tried to implement the same using YieldFSM. So my implementation has only 149, where only 40 code lines of YieldFSM, and the rest are just hyper definitions written in Clash. So the code I told you about in VHDL looks like this. So we have 26 blocks which look like this, which describe all the things related to timing, to counting the amount of time needed for each command, to outputs which happen on each stage of these operations, and so on and so on. So it's not easy to read, not easy to write, very error prone, not really thing you want to work with. And when you use YieldFSM, it becomes something like this. Show the send delay implementation because it's just a detail, right? So then the main part is here. So this initialization sequence is just the first 8 calls to send delay, where the first argument is the amount of milliseconds you need to wait, and the second argument means we send an instruction because this displays can get instructions or data, and the last argument is the kind of instruction we send. So we just state them, and thanks to Haskell, this is pretty readable. And after the initialization, we have this main loop where we just wait for commands on the bus, and when the command arrives, we just send it to the display, and that's all. It's pretty readable, I think. Okay, and another thing I did was obviously implement a RISC-V processor, and just implemented not one but 3 of them. All 3 of them are multi-cycle processors like the textbook one, so not very complicated. First one is completely textbook-like, so it just has an explicit control and data path. Another one has control path written in YieldFSM and the same data path as before. And the last one is the most experimental one, where I implemented the whole multi-cycle processor using YieldFSM. So here we have the results I achieved. So just replacing the control path reduced the size somewhat while keeping the same performance as before. And the implementation wholly in YieldFSM is quite a lot smaller, so that's a great success, but there is some performance loss. It's somewhat larger, and it runs somewhat slower, and I didn't yet found the reasons for that. It's still open question why it happened. Okay, so the conclusions. We can compile structural procedural code to media automata. I think that that's a success, right? So now we can write things like this on more readable more readable way. And we didn't lose expressivity in the process, right? So we can, all the things we could do in Verilog or VHDL, we can still do here. And the code in this language is shorter and certainly written in a style which is more understandable to programmers, which lowers the barriers to entry to us programmers in the hardware world. Okay, so there's some works I'd like to do later. So obviously I'd like to add higher order functions to this. This was only first order functions because I wanted to start simple. I'd like to formalize this somewhat. And also because yield is a kind of effect, look if this can be generalized in some way. So we look into relations with algebraic effects. So that's all. Thank you.